We are going to be delving deeper into statistical inference than you ever have before. So I thought it would be good to take a few moments to have a brief review of some of the concepts that we've learned in inference. Now, when I say we learned, I recognize that each of us have come from different backgrounds and different classes. Some of you have had me for most of your statistics classes. Others of you have never had me for any statistics. And obviously, different classes emphasize different things. So I'm just going to try to cut to what I consider some of the core foundational concepts in statistics and review those. You should not panic if you see a concept that you have not had before, because part of what I'm trying to do is outline our path forward. That is, giving you an introduction, albeit via a review of concepts that many of you have had, giving you an introduction to what's coming up, coming attractions. And these are going to be explored in much more depth. So you can think of this as an outline of what's to come. You can think of this as a brief review. You can think of this as simply a way to get us back into the game of doing statistical analysis, specifically statistical inference. Let's start by considering one of the simplest experimental designs, the two-group completely randomized design, often abbreviated as CR2. This is used to assess the effectiveness of a single treatment. So what you have in this is you have a treatment group and you have a control group. So this is the treatment, and C stands for control. And then everyone in your sample is randomized, that's what we're indicating with the R, randomized to one of two conditions, the treatment or the control. The control group either gets no intervention or, more commonly in modern research, has a placebo intervention, which I've signified here with X sub 0, whereas the treatment group does receive a new intervention. So control groups will get a placebo or a traditional intervention. If you have a new method, for instance, of instruction, and this is an educational experiment, the treatment would get the new method, the control would get traditional methods. And then afterwards, we observe everyone. The primary advantage of this is simplicity. The primary disadvantage is that there's only one method of control, and that's randomization. However, randomization is considered a gold standard. Why? Because it removes systematic bias for all extraneous variables, not just those that you can think of. If you think of certain extraneous variables that are strongly related to your response measure, you could do more specific things to control those particular variables. But there may be other extraneous variables you haven't even thought of. The nice thing about randomization is you don't need to think of them. If you randomize, you remove systematic bias toward either the treatment or the control condition, no matter what the extraneous variables are. After we have conducted an experiment and collected our data, the first thing, of course, we should do is not inference at all, it's description. We should always start by describing what happened to the individuals in our study. It really doesn't make a lot of sense to start talking about what we can infer outside the study when we don't fully understand what happens in the study. And throughout this semester, I'm going to emphasize this point, wanting you to look closely at what took place within the experimental conditions before you try to make inferences outside of that experiment. You should do this with visual analysis, that is graphical displays. You should do that with descriptive statistics, And you should estimate the size of the effect. In this case, the size of the effect might be just something like the difference in means or the difference in medians, or you could standardize that. Standardizing has the advantage that you take into account the variability. If you have two means that are different from one another by, say, 5 points in one study, and in another study, two means that are different from one another by 5 points, those could have very different meanings if you have a lot more stability in, say, the first study than the second. And therefore, you would get a bigger effect size in the first study. That would be noted when you standardize based upon the variability of those means or the variability of the scores. When you standardize that difference, then that helps you understand how big the difference is relative to random variation that takes place. When we do start making inferences outside of our study, the first thing we'll probably want to do is think in terms of a point estimate of a parameter. That is, we're going to take the descriptive statistics that we have found in our study and use them instead of describing what happened in our study as an estimate of what we think might happen outside the study. So, for example, if in our control group we end up having a mean for the control, we would think of that as an estimate of the population mean outside the study for everyone who would receive that traditional treatment or that placebo. This is a point estimate, meaning we have no confidence in it because it does not take into account at all the potential variability that you get from sample to sample to sample. That is, if I were to obtain another sample, then the mean that I have here could shift in one way or another. And that particular shift, either in a lower direction or an upper direction, that particular shift would give us, of course, a different estimate for the population mean. So it is fine as a first step in inference to use what happened in our sample as the best guess for what happens in the population. And in fact, our sample values often are statistically our best guesses. They're what are called maximum likelihood estimates, which you're going to learn a little bit about later in this course. They are our single best guess. But we also have to recognize that from sample to sample to sample, you're going to get different sets of data, and therefore the guess might change. And therefore, in any single one guess, you really don't have much confidence that you've indeed hit on the actual parameter in the population of values. Another method of inference that does take into account sampling variability is the hypothesis test. A hypothesis test is a way to determine how likely it is that our observed data would occur if our speculation about a parameter, which we call a hypothesis, is true. So in this picture here, we have a parameter that we're speculating, not because we know what the parameter is. If that was the case, we wouldn't even be doing this. But we're taking an initial guess at what the parameter might be. So here's our parameter that we're initially guessing. And then once we have the initial guess for a parameter, we take our actual observed statistic and we see how far away the observed statistic is from that parameter. The further away it gets, the least likely it is to have obtained that data if this parameter were true. So what you're seeing here in this picture is what we call a sampling distribution. That is, for all different samples, all the different statistics that we might expect to get if this parameter here is actually true. And so when we end up with statistics that are out here in the tails, in fact, let's say we got one that was even further out here. Okay, the further away we get from the parameter and the more we get into the tails of what we know to be the sampling distribution for the statistic when that parameter is the actual parameter, we end up with values that are very unlikely to observe if this is the true parameter. Possible to observe them, but not likely. Now, one thing to keep in mind here, we're not talking about the likelihood of the parameter. We're talking about the likelihood of obtaining our data. And so when you look at that p-value, that likelihood, and the p-value, of course, is, let me erase this here. The p-value, of course, is everything that is beyond this observed statistic into the tail of the parameters. So it's calculated from the probability or the area right there in our sampling distribution. That p-value does not indicate the likelihood that the parameter is true. It indicates the probability of observing what we observed, our actual data, or even more extreme than what we observed. That's all this little area out here, if the parameter is true. So when we say that the parameter is not true, it's not based on the probability of the parameter. It's based upon the probability of getting our statistic if the parameter is true. And so what we're doing is making a decision. We're deciding whether to reject or to retain this parameter here as the actual value of the parameter in the population. A more informative method of inference is a confidence interval. With a hypothesis test, we make a single guess for the parameter, and then we see if the data we observed are reasonable, or that is, relatively likely, given our guess at the parameter. And if the data we observed are not likely to be observed, but we did observe them, but they're not likely to be observed if the parameter is correct, if our guess is correct, then we say that was a bad guess. But that's it. We make that one guess. What if instead you guess over and over and over again, and each time look to see if the data you observed would be likely to be observed given the parameter that we just guessed? Well, that's in fact how we build a confidence interval. A confidence interval consists of all values for the parameter that are not rejected given the observed data when we test all hypotheses. So let me show you what I mean by that. Let's look at building this particular confidence interval right down here near the bottom because it's near the number line. It'll be easier to show. If I say, hey, I'm going to guess for my parameter 5. Okay, so I guess for a parameter 5. Now let me look at my observations. All right, my observations are very unlikely to have occurred if 5 is really the parameter of the population. So therefore, I reject 5. I say that's not the parameter of the population. I could be wrong, all right, but the chance of observing the data I observed is so small if 5 is the true parameter that it's probably not the true parameter. On the other hand, let's take a value of, say, 8, somewhere around here. And now, if 8 is the true parameter, and I look at my actual observations, my actual data that I obtained in my study, is it unlikely to have obtained that data, or is it quite feasible that I could have obtained that data? In this case, we don't say it's unlikely to have obtained that data. In this case, it looks like, hey, that data could very well have come from a population in which the parameter was 8. And so rather than reject that parameter, we retain it. Similarly, if I try a guess of 9, again I say, hey, it's very possible that I actually could have observed the data that I observed if the true parameter is 9. And so therefore, I retain 9 as a possible value, and so on. Up here, let's say this is around 12. When I get up here around 12, I still say, hey, it's possible for the parameter to have been 12 and me to have observed the data I observed, not just possible, but pretty likely to have observed those data, then I retain that. But when I get up now to 13 right here, now the probability of observing the data that I observed if the parameter was 13 was very small. And the fact that I did observe those data makes me think that 13 is unlikely. So what I have done is I have now found all the possible values of the parameter for which I did not think it's really crazy that I observed the data I observed. For all those values of the parameter, I very well could have observed these data. The probability is not real tiny. The probability is rather big that I could have observed these data. And therefore, I retain all those, and that forms our confidence interval. Now, another way that we can think of this, which is one of the outcomes of constructing a confidence interval, is that if you construct, say, an 80% confidence interval, then you expect that 80% of the time your confidence interval you construct from your data is actually going to capture the true parameter. So for an 80% confidence interval, we would expect that 4 out of 5 intervals will capture the parameter. That is, if you take repeated samplings over and over and over again, 80% of the time you're going to build a confidence interval that works, okay, that actually includes the true parameter that you're trying to estimate. So whereas with a point estimate, you have no confidence, if you put now a range on that estimate, if you now say, I'm going from here to here, rather than a single number, you're going to give a range of numbers. Now you can actually attach confidence to that. Anytime we want to do a hypothesis test or build a confidence interval, there's actually different methods that we can use to test those hypotheses or build those confidence intervals. And so some of these tests you have learned, depending upon what statistics courses you've had. For unordered categorical dependent variable in the CR2, the completely randomized two-group design, if we have an unordered categorical dependent variable, like, for instance, success failure, you're not saying that there's any order to that. Pass, fail, yes, no, anything that is a unordered dependent variable, we can use Fisher's exact test, a two-sample binomial test. In most introductory statistics courses, what you learn is the Pearson's chi-square test. So I'm not saying you have to know all these tests. You probably don't. What I'm making the point of is that we have choices. And the actual consideration of our data and the characteristics of those data should lead us to which choice we make. If we had ordered categorical dependent variables, we could do a median test, a two-sample Wilcoxon, a normal scores test. And if we have quantitative variable, we could do a Fisher randomization test or a two-sample t-test. Both of these are actually described in Chapter 1. So what is it that leads us to choose one method of hypothesis testing or confidence interval construction over another? Well, it's what we know about the data. And if we don't know it, what our best guess is about those data. For example, do we know that we have an unordered categorical dependent variable? You never have to guess at that. You know whether you have unordered categories, ordered categories, or quantitative data. This depends on our level of measurement, how we actually measure our response variable. Do you have independence of your conditions, your treatment and control conditions, as well as independence of each observation? That is actually a requirement for almost all statistical inference. So that doesn't lead us to one method of hypothesis testing or confidence interval construction, because that really is not discriminating among methods. All the methods require this. Each observation can be placed into one category and only one category. That will lead us to either a Pearson's chi-square or any of the other methods that I listed. If we have distributions in which we have identical shape for an ordered categorical dependent variable, then we will use one method of hypothesis testing, but if we don't, we might have to use another method of hypothesis testing. Is the measurement scale at least ordinal? For quantitative variables, we expect the measurement scale's at least interval. That's what makes it quantitative. If it's not interval, if it's ordinal, you can't do things like calculate means and have those means be valid estimates of the center of your distribution. The distributions have to have identical shape with quantitative variables, but for many situations, they also need to be normal. Although, as we read in Chapter 1, there are reasons to pursue normal-based analyses even when we know that the distributions are not normal. And we'll discuss that separately from this presentation. A key concept in statistical inference is that we, as researchers, can and will make errors. That is because we are trying to infer, based upon a few observations, to something outside of our study. We do a study with certain individuals, but we want to come up with general principles and general ideas and laws of how constructs relate to one another that go beyond just the specifics of our study. Remember that one of the keys to science is to be able to infer to the general from the specific. And once we do that, we are prone to make errors. There are two main kinds of statistical errors: errors of the first kind and errors of the second kind, otherwise known as type 1 and type 2 errors. Type 1 errors are usually viewed as the most serious. A type 1 error, as you know by now because you've had statistics classes, is when you reject a null hypothesis that you should not have rejected. That is, you say that's not the true parameter, but it was the true parameter. And as a consequence, when we reject a null hypothesis, for instance, that the treatment and control group means are equal, what are we concluding? We're concluding that the treatment works, and we probably will do things like write articles about that. And that's considered a serious error, as we then go forth with our reputation to say we have a treatment that works, when in reality it only worked in our study. It would not work outside of our study. Type 1 errors are said to have a conservative error rate when the actual rate is less than the nominal significance level. So if we say that we want to keep our error rate no more than 5%, Well, if the error rate is actually 3%, we're doing that. We're keeping it no more than 5%, but we're even being conservative. That is, we're having an error rate that's less than what we were willing to tolerate. The error rate is said to be liberal when the actual error rate is greater than the nominal significance level. So if I say I want my error rate to be 5%, but really it's about 8%, now I'm in dangerous territory because I'm going outside what I was willing to live with. 5% error translates to 95% confidence. And if I don't really want to put that article out there unless I'm 95% confident, and it turns out that unbeknownst to me, the error rate is liberal and really at an 8 or 9% rather than at a 5%, then I'm not as confident as I shouldn't be as confident as I think I am. Errors of the second kind, type 2 errors, are when we do not reject a null hypothesis that should be rejected. In the case of comparing a treatment and control mean, and let's say we hypothesize that there's no difference and we don't reject that, then we come away saying we're not sure if the treatment works. Remember that when you do not reject, doesn't mean you say that you have shown or proven the null hypothesis. Not rejecting just means you retain that hypothesis as one of a variety of hypotheses that seem reasonable to retain given the data that you observed. So if we have an error of the second type, we're not going to go out publishing that the treatment works. We're just not going to make progress with science because we will not make conclusions. Increasing the effect of the treatment can increase our power, that is, our ability to reject the null hypothesis when we should. Increasing the sample size can increase our power. Reducing the error of measurement can make it more likely that we'll reject when we should and therefore avoid an error of the second kind or a type 2 error. And also the choice of statistical method. Which of the methods that, such as the ones that I showed you in the previous image, which of these methods could in fact be best suited to give us a rejection of the null hypothesis if it should be rejected? So I use this term power. Power of a test is the probability of rejecting the null hypothesis when it should be rejected. It's the actual probability of rejecting that null hypothesis when it should be rejected. Whereas a type 1 error is the probability of rejecting the null hypothesis when it should not be rejected because it's true. So in this image here, I'm contrasting those. So here is a particular parameter right here that I'm hypothesizing. And this is the sampling distribution for that parameter if that parameter is true. And therefore, if I set my p-value to be low, my rejection region will be right out here. I'll only reject when there's a very low probability of obtaining my data given this parameter. And that's what allows me to keep my type 1 error rate low. On the other hand, suppose this is not true. Suppose the correct picture is this one up here, because the parameter is actually somewhere over here. Now, if the parameter is somewhere over here, then the sampling distribution will look like this. And the probability of rejecting, because remember I set the probability of rejecting based upon this picture down here. This is where I decide under what conditions I'll reject the null. So if I set it at that condition, but the true value of the parameter is actually here, then the probability of rejecting is going to be all this area here beyond the rejection region, in the rejection region. Those two big tall bars, and that's going to be the power of my test. Another concept in statistical inference has to do with what type of inference we're trying to make. Sometimes I think researchers forget that there's multiple types of inferences that they could be making. One of the primary purposes of scientific investigation is to infer general principles based on the observation of specific instances. But what is the general thing you're inferring? Who are you inferring to? A causal inference is made in a study when the conclusion is reached that the observed relationship of the explanatory and response variable is one of cause and effect. So if we do an experiment and we say that manipulation of variable A creates changes in variable B, that's a causal statement. And if we see this happening in our study, we want to be able to infer that outside our study. Another kind of inference is population inference. That's when the conclusion's reached that the observed relationship, what we observe, is actually present in the population. That is, not that it's cause and effect, but that any kind of parameter value or relationship value can be inferred to the population. We're going to explore different types of inferences a bit more in Chapter 2. Which of those types of inferences we make depends upon how we actually conducted our study. The validity of a causal inference is checked using a statistical permutation model. Your authors in Chapter 1 introduced you to statistical permutation when they discussed Fisher's randomization test. The permutation model posits that the arrangement of experimental units is one permutation out of all possible permutations. By contrast, the validity of a population inference is checked using a statistical sampling model. The sampling model posits that the observational units consist of one sample out of all possible samples. So notice that with causal inference, we don't even have to draw a random sample from the population. What we have to do is make sure we randomize to conditions. Whereas for population inference, we better darn well make sure that our sample is a good representation of our population. Here's a little illustration of these two methods for the two types of inference. Causal inference depends on us obtaining one randomization from all possible randomizations. So think for a moment that you had, say, a number of participants in an experimental study of 50, okay? And suppose you're going to put those into two different conditions. There are many, many, many ways of taking 50 people and placing them into two different conditions. And what this oval here is meant to represent is this represents all the possible ways. So here's a way, here's a way, here's a way, here's a way. All right, so John, in one of the randomizations, John could end up in the treatment, but in another randomization over here, John could end up in the control. And if you think of all the possible ways that you could put 50 people into two groups, there's tons of them. There are many, many possible ways, and that's what's being represented here. This is representing one possibility. And so what we're looking at is we're looking at one randomly selected randomization from all the possible randomizations. And that's what allows us to make causal inferences. By contrast, if you think of a population, there are tons of possible samples that you could get. There's this sample, this sample, this sample, this sample, this. So this represents the one sample you actually got right here. And that one sample there, you obtain data from that one sample, and you're wanting to infer this as a representation for the population because it was randomly drawn out of all the possible samples you could have gotten for that particular study. both the description and the inferences that we are going to do this semester are going to focus very heavily on models. And so here's a little review of the idea of model equations. That is, the response for any particular individual is seen as a linear combination of different elements. The first one being the response for an individual is going to start with a baseline, which we use the mean for the individuals, for all the individuals. So if someone has a score of 53 and the mean for all individuals is 50, 50 is the baseline. So what we now need to know is, why did that individual score 53? Well, part of the reason could be because of the condition that individual was in, and that's indicated here with this alpha sub j. But even if we add in the effect of that condition, not everyone who's in a particular condition, such as a treatment, all gets the same score. Even within a condition, people get different scores, and that's because of their individual characteristics, which we indicate here with epsilon. So this is one of the simplest kind of models that we can have, and we're going to look at model after model after model in this class. You're going to get very familiar with these. So this is just a brief review, but you're going to have this reviewed ad nauseum later on. The elements of these models are going to represent different types of effects. And so we're going to focus a lot this semester on what type of effect we have, and there's three primary types we're going to look at. The first is a fixed effects model. That is, when the levels of the explanatory variable are all of the conditions chosen for the study. So in our two-group example, the treatment is the only treatment we're interested in. Contrast that with a random effects model, when the levels of the explanatory variable are randomly chosen. So for instance, we may have multiple treatments, but we're only going to pick one out at random to study in our design. Now you might wonder, why would we do that? You're going to see that there's conditions when we would do that. And then a mixed effects model is employed when we have more than a single factor in our study, and some of those are fixed and some of those are random. So you have been briefly introduced in your introductory statistics courses to these concepts. We're going to go into this in a lot more depth in this course. Here's a little illustration of fixed versus random effects. You can see here for the fixed effects model, we have the whole population of possible effects taken up by our four conditions, whereas in the random effects model, there are many, many possibilities, and we're just picking four of those at random. Okay, that will do it for this very brief overview of some of the key concepts in statistical inference. If you've not had some of these concepts before, that's okay. We're going to delve into them in a good bit of detail in this course, so hopefully this would just whet your appetite.